Water reticulation systems, the advantages are listed there like this. You could go on about certain advantages. There's always disadvantages, but advantages are improves quality and efficiency of the water in particular. It avoids stock losses from bogging. Obviously, if you've got stock running into dams that are almost dry, they get bogged, and you'd all know about that. And more efficient feed utilisation, of which I believe what the livestock is telling me, because I'm not a livestock person, I'm more an irrigation person, but I think that gives better feed utilisation. Lee might say something about that tomorrow, a little bit later in case I'm wrong. With reticulation design, just putting a system in sounds real easy. You just whack a tank and stick a few lines in and put a few troughs on. Sounds great, and water will probably come out. So yes, you'll have achieved something, but to really do it well, you've actually got to get some professional help. You need to design the reticulation systems. They don't. A good system doesn't just happen. It depends on the application you're looking for. Where are the stock? Which stock? Where are they going to be? What's the situation you're in? The topography, and this here we are. It's got hills and dales everywhere. Just where are you going to put things? That's quite important. And location in terms of where's the water supply relative to your stock and that kind of thing. The system needs to deliver at peak daily demand. Now, Grant said he's in the containment yard. They just come and go. That's nice in a containment yard. A lot of stock, I'm told, and I'm happy to be corrected, like to sort of water at maybe like a peak hour. They all decide, right, we're all going down the pub together, have a drink. They don't just sort of one at a time go when they're out in a paddock. Now, I'm on the right track a bit there, because I've heard others say maybe that doesn't quite happen as clear cut as that. But either way, we've got to be able to deliver the water to the demand that the stock wants. And that's a concept that's a little bit vague, but that's what you've got to get in the design of these systems. And for tanks, most systems have a tank in them. The tank should be large enough to supply the maximum daily demand. You want at least one there, maybe more, and I'll mention that a little bit more later, so that you've got some buffer in case something goes wrong. So those things are important factors, and to get it right, you really need to get some professional advice. Now, I throw that out really easily. Finding that advice, finding people who can do that is not as easy. I'm fortunate in Tamworth that we've got a very good supplier who supplies irrigation and all sorts of things and does a lot of good stock water stuff. There are others around that I don't know well enough around the state. You guys down here would have a better idea than me of who to go to, and I always say the old farmer's grapevine's the best way. Go and see who's got one in and are you happy? Is it working? Find out. Plenty of people can put them in. Drill a pipe, rip a pipe in, put a tank, put a trough in, but that doesn't mean they're doing the job right. Okay. How long should the stock drink for? Well, the assumption we're making in this rule of thumb, that again is not from me because I'm not a stock person, we've got for someone else, is about 4 hours. In other words, you want to get the stock fully watered over a period of 4 hours in a day. And that is kind of setting our flow rate required for our reticulation system. We've got to get the flow we want. So Grant said he's got the stock thing in the containment yard down there, not a big trough, but he said the flow rate or supply rate is the key thing. And it is the key thing for a reticulation system. The other sizing is important too, but if you haven't got the flow rate, if you can't keep up with how fast the stock want to drink, then you're holding them back and you're going to have problems. And how can you do it? Well, you can do this rule of thumb, and you might want to modify it, others have. You find the total daily water use of your mob, divide that by 240 minutes, which is 4 hours, and that gives you the flow rate you want in litres per minute. Now, finding out the mob requirement and all that, that's what we'll do in the other part of the course that Steph was talking about, that we'd love you to come along to. But that will give you the first key item for getting a reticulation system sorted out. You've got to know the flow rate. That's required. And if I use my example, if you guys can see it, this is a little bit out of the course. If we've got, for example, dry 1,000 dry ewes, we're saying that they need 10 litres per head per day. Therefore, the total requirement is 10,000 litres per head per day. And if we've got dry cows, 100 of them, they need 98 litres per head per day, maybe 9,800 in total. If we put those two things together, for each of them, that 42 litres a minute is required, 41 litres a minute for the stock. So we need a system that'll supply about 83 litres per minute. It's all going to be give or take. It's a little bit rule of thumb, but that's giving you an important figure. You don't just go, oh, I'll stick a few pipes in and hope it runs good enough. You can actually ascertain the flow rate by knowing your stock numbers and stock requirements.
These are summer water consumption rates.
Yes, it's high summer rates. Yes, we'll go that, if we do the course, we go into that more. They're talking about a very drought, if you like, circumstance, which unfortunately in this part of the world is still almost the case. It's pretty bad. Yeah, so it'll be much less hopefully going into winter. Basic idea of reticulation system could look like that. You've got a dam or a creek or a source of water over there somewhere, pump on it up to a tank, which you'd put up on a nice high hill somewhere, and then reticulate the water to the trough or troughs by gravity. And you can put the troughs where you need to, and you should set them on a pad of some sort, concrete pad, or there's other ways of doing it, but you want it nice and firm. You don't just drop the trough on the ground, because that's how it'll end up all skewed and twisted and broken. You could use some of the same pipe work to put the water into the tank as get it out of the tank. So there's our water supply on the left, there's our pump, pumping up to the tank, and then that same water can reticulate down to the troughs. When you've got that sort of set up, you've got to make sure you've got valves on the troughs that can withhold the pressure of the pump, because when the pump kicks in and pumping up to the tank, if you've just got your ordinary pressure valves on your trough down below, it's going to override the pressure valve and flood the trough. So all that water you're trying to pump up the hill will just go out of that trough. So you might need to put in pressure reducing or pressure control valves, or even just a good old gate valve that you can turn on and off when you need to. There's any number of different ways you can do that, but that's the base idea. Pumping the water from somewhere, sticking it up high and letting it run to the troughs where you want the troughs to be, where the stock water. I want to introduce this idea too, which is not a very sort of obvious one. It says illustrating hydraulic gradient. Well, I'm going to say illustrating friction loss in pipes. Has anyone heard of friction loss in pipes? Yeah? Nodding a few heads. Anyone not heard of friction loss in pipes? Because you're all well informed then, because a lot of people don't think of friction loss in pipes. Because water actually does have friction against the edges of pipe walls. It gets warm and it needs energy to overcome that friction loss. And what this is illustrating, if this was a tank, and if there was no water moving, and we had a whole lot of pipes, for whatever reason, along our pipe work, all sitting up as high as the tank, and no water was moving, all of these would be up here at the same height as the tank. As soon as there's water flowing, we open the valve, let the water go, you can see that this is now not as high as that. And this one is a little bit lower again. And this one lower again. Now the reason for that is the friction loss through this pipe. Once the water's moving, we get friction against the pipe walls, and there's not as much energy to push the water up. We could say that much energy is how much that pipe took to get it at that flow rate. Here's a bit more energy and a bit more. Of course, if you keep going with that sort of thing, you get to a point where it doesn't actually stop, but it'll just dribble out, because you've got this friction loss that's just accumulated. It's too much, and it might be a lovely tank at the top of the hill, but it ain't coming out fast here because you've got lots of friction loss. That's part of the design process, and that's the sort of concept you want to be able to talk over with the design people, but it does come down to dollars, which is always the case. Smaller pipe, diameter pipe, costs less than larger diameter pipe. So you think it's easier to buy the smaller diameter pipe, but then you might be choking your system. So you might be losing a lot more than you're gaining. In terms of just conceiving that, what do I do if I've got a system with a tank and I've got troughs everywhere? How do I think about it? Well, perhaps just think of it as one tank, one dirty big pipe to supply the stock. I've got to have a pipe that will get the flow rate at the bottom to the stock at the rate that we already determined, those litres per minute that we worked out. And then if you've got multiple troughs, then you can start to divide it. If you've got 2 troughs, well, you've got to have half the flow here and half there. Maybe the pipe size, you can come down a bit. Or 6 troughs, you can bring the pipe sizing down a bit. But you've got to start with the pipe big to get that flow rate that you want to get the water to the stock in the time they need. Otherwise, they're thirsty. First point I got there, I already mentioned, friction loss adds to the pressure required. So that nice big tank up the top of the hill, yep, if you've got skinny little pipe all the way down the bottom of the hill, it's still going to dribble out, no matter how high up it is. Smaller the diameter increases the friction loss. So what you should do is approach designing for the largest diameter that you can, largest economic diameter. Don't go over the top. Just think, yes, I need a bigger pipe. Generally, people who've got bigger pipes in the end are happier than those who've got the smaller diameter pipes. Length increases friction loss. If you've got a certain amount of friction loss going here, well, if you double the length, you've got double the friction loss, and so on and so on. So the longer the pipe, the higher the friction loss. So try and pick the shortest practicable route for your pipe work. And a bottom point, fittings. If you've been to the shop, you see what they like, all those sort of poly fittings and things. They're different prices, different sizes. All the pipes and the fittings are pressure rated, which means they're rated to work to a maximum pressure. And if you work at operated above that maximum pressure, you're going to blow a hole in it. The fittings are always more expensive than you want them to be. Pipe's bad enough, fittings are worse. You see that fittings of a different price, you think, well, that fitting still fits my pipe, I'm going to go with that one. But if that fitting is lower pressure rating than your pipe, guess what's going to happen? When the pressure's on, the fitting's going to blow. And you forever have trouble with these fittings. And you think, what's wrong with these things? They're dud fittings. Well, no, they've probably just been wrongly chosen. The fittings have to have the same pressure rating. That's a thing all round, again, for design. The design of the system works out what the pressure is required and makes sure that the appropriate components are selected to not have a failure. And we will do a little demo shortly when I finish this, just to demonstrate the pipe friction loss for you. But here's a few tips. These come really from my friends at Tamworth who do a lot of this. They get sick of doing stock water systems and having to get called back to fix up problems that occur. So they have themselves set some rules that may not be the actual design-wise, it might not be needed, but they're saying practically wise, we're not going to do it any other way because we're sick of being called back to fix up these problems. So if you don't want to do it this way, go to someone else. They say use bigger bore pipe. The bigger the better. With the pipe, all our pipes starting out at whatever size they are, they nearly all will get some sort of deposit inside them. Even a microscopic little bit can upset the friction loss, increase the friction loss. But if you start getting calcium carbonate laying down or iron bacteria, if anybody's experienced that, anyone come across iron bacteria?
Red sludgy stuff, isn't
Yep, red sludgy stuff. It's horrible sort of stuff. If it starts lining your pipe or other things that are in the water, it's doing 2 things. It's making the pipe rough, and 2, it's reducing the pipe diameter. All right? It's reducing the pipe diameter, increasing the friction loss. So these guys say they're going to use at least 50 mils. bigger you can go, the better, because it allows for some build-up. It gives you some buffer room. And they also say, just in particular, they found problems happen kind of at the starting points. Where the pump is, at the bottom where you're going to go up to a tank, they're going to use a bigger size than the rest of it, because that's where a lot of issues occur. So, for example, if it was a 50mm system, they're going to put 63mm pipe for the first length coming out of the pump. And at the tank end, they're doing exactly the same. The length that's going into the tank is going to be 63mm diameter. They say they have too many issues, and I think it's to do with the way fittings are put together, the way things might end up bending or sagging or convoluting. They just say, no, we're doing that. The design doesn't necessarily require it, but we're doing it because it just avoids so many issues that we have to come back and fix. So that's their tips with pipe size. Just to touch on tanks, obvious, locate tanks at the high point, because that's where you get your gravity. I'm with Grant, I like pencil and paper and gravity. It's great, simple the better. Get the tank up high, as long as you can do that sensibly and safely. There's some topography, of course, that you wouldn't want to touch with that. But importantly, put it on a level site and don't cut and fill. It's tempting on a steep slope to think, well, righto, I'm going to get the dozer or something up there. I'll cut a chunk out of the side of the hill, and the dirt I take from that, I'm going to pack down on the downside slope of the hill and fill it. Cut and fill, like you might do with your houses sometimes. If you're building a house, you cut and fill sometimes to get the block in. Well, don't do that. I don't know whether you guys can see that very well. The reason why you don't want to do it is, no matter whatever you do with that fill on the slope, it'll never be as compacted as the stuff you've cut into, which means ultimately it will compact a bit, and as soon as it does, you haven't got a flat base for your tank, you've got a tilted base. If it's a plastic tank, then you've got it all warped out of shape. If it's a concrete tank, it's putting stresses that might lead to a crack and things like that. So costs more to dig into the hill, put the waste somewhere else. Don't do cut and fill. Normally you are annoyed by that in the end. I mentioned a bit more capacity. You want at least have capacity for 1 day for your stock, just in case something happens. But here's some other rules of thumb to do mainly with the power supply, the energy supply to the pump. If you're on mains electric power, it's great. If it's mains is there, beauty, use it. You're still going to want, say, 3 day supply. How many people get blackouts and, you know, it takes a while for the guy to come and fix it, or a burn out of the motor or something? It could take 3 days to get things sorted out. Your stock need water during that time. If you've got solar, solar's wonderful, except when it's cloudy. So you might need 5 days supply, because, you know, what are you going to be doing? You know, trying to blow the clouds away? I don't know. If it's engine driven, as in you've got a petrol driven or diesel driven pump going, you might need to have 5 days supply. Why? If it breaks down, got to get the local bloke out to fix it, and he says, oh yes, you've blown this part, I've got to get that part from Japan, it's going to take, you know, this amount of time to get over here for me to get here and fix it up. So you want to have water available for the stock. So try and have 5 days supply. And windmill, well, there's not that many windmills around these days, but windmills are slow fellas, and if there's no wind blowing, I don't know how often that happens around here, up in our way we get some still days. Well, if it doesn't blow, you're not getting any water. So you need to have the buffer supply in the tank. Now they're of course all just rules of thumb or guides, and what it's trying to say is allow for the downtime if something goes wrong, so that your stock are not suffering. And tanks do cost some money. The bigger you go, of course, the more expensive it is, and if you're on the hill, the bigger the excavation. One of those things, though, I've never heard anybody complain about having too much tank capacity. They might complain about the price of having to get it, and they sort of do that once and then forget it. Other way around, people skimp a bit, say, oh, I saved a few bob, just I saved a few bob, they're happy about that for a few weeks, and they've got 20 years of irritation. And they, gee, I wish I'd put a bit more. Go for the bigger tank if you can. for a number of reasons. What does Paul say? What do you
Buy
say?
once, cry once.
Yeah, buy once, cry once. Yeah, that's it. Then you're happy.
And the bigger you go, the cost per litre it just goes diminished.
It does. Yep. You've got to get troughs. How much trough capacity do you need? Again, Grant was saying he didn't have a big trough down there because really the stock are contained and they're just going and having a drink when they want. That's great. He doesn't need a big trough. He does need a good supply rate. That's still the key thing. When you're out in the field, you still need troughs. Think about trough capacity because they're going to walk to get there. They haven't got the luxury of the water sort of on hand. So rough guide, 5 litres a head for cattle, 1 litre a head for sheep, 5 litres a head for horses of trough capacity. Now whether you have that in one big trough or several smaller troughs, that depends on what you're trying to set up, but that's just a guideline for the amount of trough capacity you need. Again, the temptation is to go for smaller troughs because they're cheaper, but you might be having that competition for water at the trough with the stock. So that's a rule of thumb or a guideline to work that out. And I've just, in this instance, extended that table I showed you before to say what trough capacity do we need for our 1,000 dry ewes. Well, we need 1,000 litres of stock of trough capacity, and for our dry cows we need another 500 litres. That will vary, but it's getting you in the ballpark. It gives a starting point to talk to designers or suppliers about. And troughs can service a fair few stock, but you have to set them right. And I'm very happy to be corrected by those of you who are stockies who do this. But again, rule of thumb, 1 metre length of trough can service 30 cows or 130 sheep. Does that sound like I'm in the ballpark or way out of the ballpark? Need a decent length. You can make 1 trough serve 2 paddocks if you've got a fence line in the middle like this diagram showing us. I'm told you want to locate the trough centrally because that's better for grazing. Stock don't have to move so far and all that sort of thing. Somebody in one of the courses that we did also said he learnt to put the trough up a hill. Because then the water, if it's downhill, the stock are always moving down there. Rain or other stuff will go down the stock paths and you'll end up with a boggy mess where the trough is, because that's where they drink. If you go uphill and you get a few leaks or a few other things, the water's running away. So it doesn't have such a boggy mess.
And plus when it rains, Peter, I think you said as well.
Yep, the rain sheds instead of
Rather than
concentrate. Yep, great. And again, rule of thumb, stock should range about 3k on flat ground, 800 metres on country like this, maybe. Sound fair to you guys? Work here? In other words, you don't want them walking too far because it burns off the condition. You don't want the water too far from them. And for sheep, long, narrow troughs are better because they're less likely to fall in and get stuck. It's always a hard one to know what to do with lambs and sheep, or whether you've got sheep and cattle together. But you can get different sized troughs to suit them. You certainly don't want them in. You might want to use trough guards. Pumps. People love to get carried away with pumps. There's only 2 things that you need to know for the pump. One is the total head. That's the pressure it's got to work at. The other one is the flow rate. We talked about the flow rate a little while ago. We can work that out by our 4 hours watering time. We can get the litres per minute. The total head, how high is that tank? How high is the hill it's on? And what's the friction loss of the pipe? More or less, that's the pressure that's got to be overcome by the pump. They're really the only 2 things you need to know to select the pump properly. And there's lots and lots of pumps out there. And if you've already got a pump, chances are it might do the job, might not do the job, but if it does do the job, it's probably not doing it very well. In other words, using more power than you want it to. Have a go, and if you're not pumping very much water, probably doesn't matter too much. But if you've got a lot of water, then get a pump to suit your duty. In irrigation world, which is where I mainly work, always give that advice. Don't use the pump you got in the shed. Don't use the one the neighbour wants to get rid of at the clearing sale, and don't get the one that's on sale at the pump floor. Almost certainly be wrong. Cost you a lot more in the long run than it will initially. Pumps are not really that expensive. So 2 points there is you can know quite reasonably the two key points, the flow rate and the total head, to talk to the designer about and get the pump to suit the job. And the pump's the thing you pick last. You don't pick the pump first, you pick the pump last once everything else is worked out. And they need to be set up properly. Don't do a slack job. I mean, you can do whatever kind of job you like. Do a slack job, you'll end up with a pump that's going to fail. So all the sort of things that make sense. Secure footing, align all the pipe work and everything properly, fitted properly done up, gaskets, etc. You don't want, if you're pulling it out of a stream, you don't want the pump too high above the water level. Otherwise you get cavitation occurring, and there are limits to that which can be designed in. You don't have to guess. Minimise the number of bends. Have a constantly rising pipe. That's the air purge. Use a large diameter suction pipe. One of the most issues that happen in pumps, if they're centrifugal pumps, is on the suction side. People have got pipes that don't suit the job very well, and very often they're too small. So if you've got a 63mm pipe on the outside here, you might want 100mm, 150mm suction pipe on the suction side. It just saves so many issues. And bottom one, valves. Don't open them fast. Open and close them fast. You get this water hammer thing, and it creates issues, a pressure wave on all of the system. If you're going to want to work out what the limits are in terms of getting something to blow, do that. Turn them off, on and off fast. But always do it slowly. And with the power supplies, we've talked a little bit about them, guys. You probably know this already, but electric's always easier to control than non-electric. If you've got mains power close handy, great, that's the thing to do. If you haven't got it close handy, forget it. To try and get a pole there costs tens of thousands of dollars. It's not worth it. Solar power is okay, but you've got to have, it's only daylight hours that you've got. You haven't got 24 hours. You've got to size things proportionally. And of course, if you've got cloud, you've got trouble, as I mentioned before. You might need a battery. Petrol, diesel are okay, portable and easy to up and down the speed if you need to, but they're usually more expensive, and you've got to cart fuel to them and that sort of thing. Then we've got wind power, where we've got various degrees of wind generation or windmills. There's not too many people I know who are going for that for pump use. Here's a good little tip at the bottom, again from my friends at Tamworth. Not all pumps have this, but some do, where you can plug in the portable Jenny into the pump. So if you're going to go for solar power, cloudy day, had several cloudy days, what am I going to do? Well, if you've actually got the old Honda Jenny or something, and it's got the plug in the pump, you can plug it in and make it pump up. So not a bad idea, just make sure the pump has that ability. A couple of other tips. You would have hopefully noticed in that first diagram early on about the reticulation systems that we've had on one of them there, we've got two outlets to the tank. So in this case, the water's going into the tank, it's coming out of the tank. And this is, again, from my friends at Tamworth, they've found so many issues over the time. What they do is, one's at the bottom, one outlet from the tank's at the bottom, another one's about halfway up. Both got valves on them, turn them on and turn them off. And what they do is they have the bottom valve shut, the top valve open. So the water can go in and fill the tank, that's fine. Can come out of the tank and go to the troughs, that's fine too. It's a lovely fail-safe though, because if something, I think Grant might have said it, that had one that drained away, he disappeared. Had a trough down there that broke and the water nearly got away, and it's just the fact that had a second dam, he was all right. Well, that's exactly what this is about. If you have a failure in the trough or the pipe or something somewhere, then it's going to drain the water, but it's only going to drain half the tank. So then you go and fix it up and you go, I've actually got another day or two or whatever it is in the tank for the stock. And if you're doing that in the middle of a drought in summer, that's going to be a real lifesaver. for not much extra cost. That doesn't cost a real lot to sort that out. I thought that was a really good tip. Another thing these guys do is put an air valve at the outlet of the pipework, at the tank. If you get the water going down a big hill like you might here, it can get quite a bit of energy in the pipe work going, and if it's sunny and hot and you've got poly pipe up exposed, that pipe can flatten. You know what poly pipe's like, it's a bit of a nuisance. Well, they put an air valve to let the air get in rather than flatten the pipe, because that could permanently reshape the pipe and then choke your system again, because it's like, you know, you flatten it down. And bury it deeply. Now, I noticed that Grant hasn't, there's some pipe down there that he hasn't buried. He's probably happy with that. But these guys had so many callbacks where, because guys want to rip it in not too deep, they only want to go 300, whatever it is. Poly pipe being what poly pipe is, when it gets hot, it twists, it moves, it convolutes all over the place, and they've had it in the ground pop out of the ground and cause all sorts of issues. So these guys say, we're putting in at least 450 millimetre. Now that costs to rip into 450 millimetres, especially through some heavy country. You need a decent sort of dozer, you've got to be able to get it done. It's not cheap, but they're saying, if you're not going to do that, we're not doing the job, because we're sick of coming back to have to fix up a job, a warranty job, as they like to make it, because it's popped out of the ground. So bury it deep is one of their tips. As deep as you can reasonably do so. And I think this is just about the last slide. This is one that Paul put together. I'm not trying to go through this in enormous detail. We'll do it more if we're in the course, a little bit more. But it's just to say, list things out, get some prices, see what's involved. You don't go, oh, I need to put a stock water in, right, I'll buy a bit of poly and I'll get there, I'll rip her out and have a go and see what happens. Sit down, plan it, cost it. Costs, like anything good, it costs, and you need to give it a bit of planning, work out how you're going to do what. Even talking to the people with the ripple tanks, say, can you do these fittings and all that sort of thing. So it's a bit of a plan to achieve an important goal, which is to be able to supply the water to your stock when they need it, at the rate they need it. So that's a reticulation system in a very quick nutshell. Just want to show you is the difference of the pipe diameter to how fast the water flows. What we've got here is a bucket of water. We've got two different size bits of pipe, plastic pipe, which you'll see is quite obvious. And we're just going to let it siphon out, so it'll be like the pump. You can see how quick it's going to fill the buckets. So if you come and stand around, you'll be able to see it pretty easily. So imagine if you had two equal mobs of sheep. The fellas at Paul's bucket, they're real happy because they got the water at the rate they want. The blokes at my side, they're all going to be fighting for the water because it's just not coming through fast enough.